All right, let's look at the first situation when we have the kinetic friction, and there's this constant we call the static coefficient of friction. We write it as this with a K. Call this one the static, not static, but kinetic coefficient of friction. For instance, let's say we have an object on a rough surface. This is a rough surface. And then we have a box on this surface. This is the box. And then this box is m kgs. And then there will be some force pulling it in this direction. Now, because it's a rough surface with the friction, the moment this force is in, immediately on the opposite direction, friction force sets in. So we have Ff. I'll use Ff to mean the friction force, and I'll use this Fx to mean the force on the x direction. So let's see what will happen. Remember, when we don't have this system moving at all, it means both this force on this direction, which is the F on the x coordinate, and the Ff, the friction force on the opposite direction, both of these forces, it's zero. So according to Newton's first law of motion, we'll say that the sum of all the forces, Fx, we get to be zero, because meaning it is stationary and it is not moving. And if this system start moving in a given direction, let's say taking the right direction to be the positive direction, it means Newton's second law of motion sets in, and then the sum of forces around the x is not a zero. It's not a zero. So we're going to have this one, f of x, that is the F net. F net means we're going to have some net force, or we're going to have unbalanced force, or we can also call it a resultant force in the x direction, and that will be the Fx, assuming it is the bigger force now, subtract the friction force on this direction, Ff, this is what we call the F net, should be equals to the mass of this object, and then multiplied by the acceleration around the x-axis. All right, that's it. So we're going to investigate now a situation where we have to account for these forces. How do we get the Ff, which is the friction? So just to make sure you don't forget, the Ff here stands for the friction. This is the frictional force. You can just call it frictional force. And then the Fx here. So the Fx here refers to the net force, net or resultant force. All right, how do we get the frictional force? We start there. So let's talk about the concept of free force body diagram. So for the free force body diagram, it's usually very important so that we can see how many forces are acting on the system and which are these forces acting on the system. So we have our box again of mass m on the ground. So this is the box, and then it will have one of the forces acting on this direction. We already have this force, we call it force on the x direction. We have this other force acting, let me make it shorter because that would mean it is less. So we're going to have the system moving towards the right direction. This is F for the friction. And then we have the force moving up. I like again drawing all the forces from the COG. So we're going to have force up, we use N. That is normal reaction force, which is the counter force for the force facing down, which should be the Fg. Now this is the normal reaction force, and this one is the weight. So on the y-axis, using the system, the Cartesian coordinate system, this is the y and the x. So we'll not have the system moving up or down, and therefore simply that is zero resultant forces along the y, but on the x, assuming the system moves to the right, we're going to have a resultant force on the x-axis. And therefore, we're going to say here the Ff, that is the friction force. How we get it, the formula we use is this formula here, where this is the kinetic coefficient of friction, and then you multiply by the normal reaction force. So this one will give us the friction force. Now, for an object that is horizontal on the ground, remember that N is equals to mg. So that is the normal reaction force is equals to weight whenever the object is just on a horizontal ground, because we don't have any resultant motion along the y-axis. So, and that makes it very easy, because that means the friction force Ff is equals to mu k, and then you multiply by the mg, that is times mg, and that gives us the friction force. Now to combine and get the force now, the net force from the Newton's second law of motion, and calculate that is the acceleration, we'll say the F net is given by, so we have the Fx, which is any given force pulling the system to the right direction, and then subtract the friction force, and this should give us the mass times acceleration. This is Newton's second law of motion. So we just substitute in the given values that we know. We know the friction force is now given by this. So minus mu k mg is equals to max. Now for this, if we integrate the acceleration along the x-axis, this simply means, therefore, finally our acceleration will be given by, divide both sides by the mass, so this side by the mass, and the whole of this side by mass, and this cancels. So ax ends up being, that is fx minus mu k mg over mass, and that will give us the acceleration along the x-axis. So that's problem number one, that we can see a simple situation when the object is on the ground, and this is how we do it. So given the mass, let's say possibly the mass is 5 kilograms, and possibly the mu k, which is the coefficient of kinetic friction, is about 0.2 depending on the surface. G is a constant, meaning acceleration due to gravity, which usually is 9.81. And then you're given the f of x. Let's say it's something like 100 newtons or 200 newtons. You can be able to see what will be the acceleration of the system. So let's take a look at this example where we have a mass of 5 kilograms resting on a horizontal ground. So how do we calculate the acceleration for this system? So we will use Newton's second law of motion. So here we know we're going to be using Newton's second law of motion that says F net, that is equals to mass times the acceleration, and this is happening along the x-axis. So therefore, first step, we draw the free force body diagram. We're going to have, of course, the weight is acting downwards in this direction, that is our mg, and then we're going to have the force up, which will be our normal reaction force, and then we will have friction acting in the back side, which we're going to write as ff. So that's the free force body diagram. So the next step from here, we just using the Newton's second law of motion, we can say, all right, let's see. We need to find the F net, and we know the net forces is along the horizontal direction because the system is not moving on the y, and therefore we're going to have the F net here is equals to the 150 newtons, that is this force, and then you subtract the friction force, the FF. So that will make our net force here, which should be equated to the mass times the acceleration along the x-axis. Now, how do we find the FF here? So FF, again, which is the friction force, FF is got by, again, remember, the mu K, and then multiplied by the normal reaction force. Now, assuming the mu K, which is will be the static coefficient of friction, for this system, let's give it to be the mu K. Every surface has its own static coefficient of friction. For this one, let's assume it's 0.2. Just assume that is the coefficient of friction. So what that means is that we can get now our friction force. Again, in this situation, because there's no net resultant force along the y-axis, it therefore means the normal force is equals to the mg along the y-axis. So this is along the y because we don't have any net force along the y-axis. So therefore, we can say this is mu k, which is equals to normal reaction force, which is m and then g. So with that, that means we can substitute in our mu k, which is 0.2, and then multiply by the mass, which is 5, and then multiply by g, which we're going to take as 9.881. All right. So if we put that one in a calculator, so we can see what value will be. That's that. That will be the friction force acting on this system, 9.81. So therefore, with that, we proceed on to calculate, or that is to find our net force here, which will mean it is equals to our net force is 150 now, subtract 9.81, and then we equate this to mass, which is 5. So 5 times the acceleration, then x. And this simply would mean, this give us what? This will mean our acceleration x is equals to, we divide this side by 5, we divide this by 5, we'll get 150 minus this, and this will be divide by 5. And once you divide this, it should be, so you can say it's approximately 28 meters per square second. That will be our acceleration. So that's a simple situation again of how we can apply this concept and have that calculation.